Hello, I am Kierian Umeayo, and it is my pleasure to welcome you to this edition of NASENI Milestones. Some weeks back, we brought you a program on the activities of Engineering Materials Development Institute, EMDI, Akure, where we did a spotlight on design, equipment, and spare part manufacturing, iron casting, and mold making. Today, we'll revisit EMDI Akure to present some other aspects of the Institute's successes, especially in research and development, made possible through the use of sophisticated machinery in the various laboratories at the Institute. They include mechanical testing laboratory, physical, metallurgical, polymer, electronic computer, electrochemistry, microanalysis, and optical microscopic laboratories. These are scientific enclaves where Nigerian scientists carry out tests for different purposes. We'll as well keep you abreast of production of furnaces and their application in the manufacturing process and other scientific and technological activities at the Engineering Materials Development Institute in Akure. Thank you for joining us. Our first port of call is the Mechanical Testing Laboratory, where physical tests on materials or products are carried out in line with International Organization for Standardization.
This is one of the machines in the lab, and this is called Universal Tensile Tester. This machine is basically very important to the production sector and to the economy in the sense that it is used for physical and mechanical property evaluation of different materials, be it fabric, even the thread of your clothes, to eggshell when you are in the agricultural sector, even to peels of banana, of orange that is being used when you are designing machines for processing purpose. And it's also very important to determine the strength of materials that are used in construction, especially with the advent of collapsed buildings all over the country. Some of these materials have been used are just sourced in the market, which are not tested, and they have been sold by roadside vendors without proper mechanical knowledge of what the material can actually carry and the weight it can bear and what cannot be bear. The machine is typically having the tensile test piece already fixed on it, which is a already machined tensile piece, and from the manufacturing sector or the machine shop, after it has been fixed on the jaws, on the clamps, and clamped together, then you go straight to test it. And in the process of testing it, it's a software control machine, and you can see on the computer as the test goes on, you begin to see at what length or at what rate the machine begins to fail. And if you come over to the machine at this place, you see that the sample begin to thin out, telling you that it's all about to fail, and which you can see now at this point now it has failed. And that also corresponds to what you can see even on the graph by the software that is being shown on the computer here, and that has shown that the machine has actually, the material has failed. And having failed, you can now use this to explain or to know, okay, if this material is of standard. And that is why this machine is very, very beneficial to the Standard Organization of Nigeria, because of the different importation of different things that are coming to the country, and they can now know if they are actually up to the standard. And also the Manufacturing Organization of Nigeria can also key into the use of this machine to actually upgrade what is being produced locally and to see if it can actually meet up with the international standard.
But here is another machine in this mechanical testing lab that can give a complementary data to the instrument machine, which is called the hardness machine. It's also a mechanical testing machines. It also helps us to evaluate the hardness of materials. Take for examples, let's take for example the glasses, the car glasses, the wristwatch glasses. We discovered that some of these things, if they fall down, all of a sudden it shattered into pieces. What is happening there is because the hardenability is very low. The hardenability is very low. What this lab is giving us a green pictures to be able us to ascertain, particularly using this machine, will give us the pictures to be able to ascertain the particular hardness value of that materials. Upage principle says the finer the particle size of any materials, the better the mechanical properties. Take for example, typically, most especially the hardness of that materials. If the particle size of any materials are fine in nature, take for example, if you take it to a nano level, you discover that the particle, the materials, the mechanical properties of that materials, that is the hardness value, we have a very good value. And when the hardness value is appreciable, the materials will be able to resist any shock or any form of force being placed on it. So all our wristwatches and some glass materials, metals and non-metals that are mirror-like in nature, you can access the hardness value. You can access the hardness value of that particular materials using this machine. And how do you use it? You make sure that the materials pass through the metallographic lab, where they section the materials using the low-speed cutting machines in order to not to tamper with the chemical composition of that materials. After using a low-speed cutting machine, they take it to a mounting machine to mount that samples in order to enhance good textures or good handling. So from there they take it to make the grinding and polishing, where the surface of the materials is mirror-like, because this is a micro hardness. Why is it micro? It indents the microstructure, the internal structure of materials, by giving us the hardness. How does it work? It works with the uses of indenters. What you are looking here is the indenters. This is the indenter, where this one is the lens. So when you indent it, click start, the materials will indent, and then after indentations, the lens will come and view the particular structure of that materials. So after viewing the particular structure of that materials, there will be a particular regions where the machine will capture and give you the internal structure of that materials by revealing the hardness value. As you can see displayed on the dashboard of the machines, it shows that the hardness of these materials is 123.9 vicars. So from there, and there is a template ASTM standard for every samples of these natures. The ASTM standard, what is it telling us? Is giving us that this is a particular range where the range of value the particular materials must fall into. So if it fall within that range, then you can recommend that materials in service, that these materials will be able to withstand any shock.
Next is the physical metallurgy laboratory, where microstructural analysis is done to determine the specification of materials produced.
This is physical metallurgy laboratory. In this lab, we prepare our samples for microstructural analysis. As we know, microstructural analysis will help us to know the specification of any material that we produce. When we view this microstructure, the structure of the materials have relationship with the properties. The properties like the toughness, like ductility, and maybe the strength. So with this microstructure, you'll be able to relate the properties properly. And at the same time, it will show you the area where you are going to apply that particular materials. This is our low-speed saw with the blade that we use to cut the sample in order to be able to handle it for grinding. After the cutting, in case the sample is too small or is not handy for grinding, we will now make use of our mounting press. This is the mounting press. We use it to mount the sample. If the sample is too small, that you will not be able to hold it very well, because when you are grinding, it will be conducting heat. So for you to be able to hold it, you have to mount it. This is the phenolic powder that we normally use for the mounting. And we have a mold inside this machine where we are going to place the sample and apply the powder. Then apply heat. After some minutes, you discover that this phenolic powder will cake around the sample. Then you'll be able to handle it properly for grinding. After the mounting, then we move to the grinding. This is our grinding machine. What we do with this machine, we normally use it to grind the surface of our sample before we view the microstructure. And before we start using it, we have various emery papers of different grit sizes, ranging from the coarsest size, which is size 60, then followed by 120, 240, 280, until we get to the finest one, which is a grit size 4000. So we start with the coarsest one because it's just like a sandpaper. You want to polish the surface of the sample. You are now going to put it on the machine. Then it will be held. Then we grind it properly. Then when we are through with this size, we go to the second one, which is size 120. Then followed by 240 until we get to the finest one, which is grit size 4000. And that is the finest paper that we use. By the time you get to that paper, you have gotten a very fine and mirror-like surface, just like this. Then after this grinding, we now move to polishing. We come to polishing machine. This machine is just like the grinder too, but the paper we use is called polishing cloth because it's very fine. With this polishing cloth, we are now going to add a diamond paste. It's in form of paste. Then we apply the paste on the surface of our sample. Since we have a flat and shiny surface, we apply it on it. Then we polish it. By the time we finish with the polishing, we'll be able to get a mirror-like and a shining surface where when you now etch it with the chemical, you'll be able to see and view the microstructure. And this microstructure, I've said the other time that it will help us to know the type of the application, the area where you are going to apply these materials. You know, in most cases, those people that are doing bridge or the reinforcement of the house or all those things, they will need a material that will help them to be able to, that will not collapse on time or that will be that will not fail on time.
Engineer Ajay Christopher takes us through the process of fabricating electronic devices in the Polymer Electronic Laboratory.
This is Polymer Electronics Laboratory. This is where we fabricate electronic devices ranging from light emitting diode and even solar cell. Particularly in this lab, we fabricate solar cell. So this is an example of a solar cell fabricated here in EMDI. So this is the solar panel that we see out there that supplies the homes with electricity and other. Start from a cell like this, being developed in a lab, in a research and development lab like ours. So this work, what we're working on, you can see is a solar cell that's evolved a lot of high technology to achieve this. So basically, we prepare the samples. There are a lot of materials that is being used to produce solar cell. Oxide materials, zinc oxide, titanium oxide, and you can name it, a lot of materials like that. So in a lab like this, we prepare those materials, then we have a lot of equipment that we use for the preparation. The solar cell that we prepare here is based on spin coating method. We have a spin coater that that deposits the materials on a glass head like this. So we mask it and give us the shape that we actually have here. So now, in this station, this is where we test that solar cell to see how the device is working, to know how efficient it is. So here, we just test the equipment with what we call 4-point probe. This is the 4-point probe. That's 4 points where we test the materials to check the voltage current characteristics. It's a solar cell. It's going to absorb the ray of light, convert it to electricity that we use in our houses. So we have to test, and then this equipment here is called solar simulator, because we are in the lab, we are working on a solar cell. By the time we finish the solar cell, should we just go out in the sun and test it? It may be somehow cumbersome. So we have a solar simulator. It will emulate the radiation of the sun in the lab. So we put the cell here and try to shine the light on it, and at the same time test to see how the cell is working, to see the efficiency of the cell that we have worked on. So this is the station for the 4-point probe. Inside the probe, we look for 4 points on the cell. Look at 1, 2, 3, 4 points. So when we get the 4 points on the cell, we look at the current and voltage characteristics of the cell that we have built to see how effective it is. So this is the interface system, and then the software that interfaces this machine is called Lab Tracer 2. You can see Lab Tracer 2 is it. By the time we get here, I just say, okay, custom duty, because the device is under test. So we use device under test, and then our version of the 4-point probe is 2400, and by the time we now run the test, so we get results like this: current, voltage for a particular cell, for a particular material. So we have, see the graph. It will tell us how the device is working. Is it absorbing enough solar radiation? Can it provide enough electricity to the home? So we have a lot of results here that is presented.
Sieve shaking machine is an equipment in which analysis of different materials, such as sound, soil, food, and chemical products, are being classified into different sieve sizes. We have different sieve mesh from 38 microns to 650 microns. Each micron has each particle size that can be retained on heat. The lowest particle size has the finest particle structure, while the highest, the 650 microns, has the most coarse particle size. In the production of mortar, making use of ceramics, where they want to produce mortar clay, using clay materials for production, normally they make use of the most fine particles, which is like a 36 microns. Why are we making use of it? Because it has a fine particle. The surface will be clean, the surface will be fine, there won't be impurity. Okay. Also in the construction industry, where they make it, where they dualize road, where they construct roads, they make use of sand. And now the material they are using has different particles. There are pebbles, there are other impurities. It is through the use of the sieve shaker that these things can be differentiated. But now we are going to demonstrate the process involved, how we can use it. This is a silica sand. This silica sand is being used on the foundry, So for plastering and doing all of that things. This is the particle size. We have different particle size there, but when we add it to this sieve shaking machine, it will classify it into different sizes. We make sure that we cover it so tight so that when the equipment is working, dust will not be able to escape. At the end
for today. We untie it because hopefully we believe that it will have each particle, each mesh will have particle size will have been retained in each. So here it is. This is the most coarse particle size. Then lastly, this is the 38. If you touch it, it's very, very fine. So we can't compare it. But all the mesh sizes are good for its own purpose. Some industry may need the most coarse part, while some industries may need the finer part.
From all indications, Engineering Materials Development Institute, Akure, is one of the key research institutes under NASENI that has proved that with homegrown technology, our nation can achieve a self-sustained economy and can be more independent and powerful. At EMDI and indeed other institutes under NASENI, we have a pool of talents and expertise that would transform the country through science, technology, and innovation. We call on the private sector, especially the small and medium enterprises, to partner with NASENI on its research results and products made by the institutes. These goods need to be adopted for commercialization and mass production for the benefit of our Nigerians. Let's now have the Executive Vice Chairman, NASENI, Professor Mohammed Sani Haruna, to talk to us on EMDI.
The center in Akure is basically established to look at new, existing, and even emerging materials. It is a material research and development institute. The idea is all new materials, composite materials, combination of different materials to give a new product should originate from Akure. In other words, if NASENI center elsewhere is doing a product development, the specification of materials that should be pitted or the alloy of materials or equipment that should be, we are supposed to have that assessment and grading and credibility tests and acceptance from Akure. The institute is doing a lot of things in the area of nanotechnology and advanced materials. And it is from that institute that we started our small hydro products or small hydro turbine development. In fact, the success of that center has made the UNIDO, United Nations Industrial Development Agency, to accredit that center as a center of excellence for training of small hydropower in Africa. And several countries of Africa came to that center at different times over the years since 2013 for training in small hydro development. From that center, initially we learned how to do small hydro turbine from Indonesia. A center called HICOM in Bandung, Indonesia, trained our experts on how to do this. Of course, our experts were trained in China also and in South Africa. But the most effective training is the one we received from India. And from that, we learn and doing exactly what the Indonesia taught us in small hydro turbine, cross-flow turbine that of course depend on the power generation in that defense of damming, depending of working on the principle of potential, that is height, pressure of water to turn turbine. As a result, we learned another technology from Belgium. We saw a technology that is used for a different purpose, for small ferry in the river and small boat. We convert that technology into kinetic turbine, which generate electricity based on flow of water without disturbing the structure or construction of any dam or height, natural flow of water. It is also done for us, the reverse engineering of that of products in Akure. Akure is because of the expertise gained in these two production, has innovated what we call propeller turbine that generates electricity also easily based on interruption of water flow to public water supply. The main supply, you can install a turbine, and as the water is passing by, it generates electricity. This model of Akure, the first version, which is 10 kilowatts, is installed in installed in our dam in Ikare in Ondo State. The first version of cross-flow turbine is the one that is installed in Ile Ijesha in Osun State. So this Akure has achieved, and it is there we experimented the materials of our solar cells, the substrates, the different model, and even the high efficient solar cells we are now introducing in order to have high efficiency is actually experimented and produced in Akure.
And that's our package for today. We appreciate your viewership. Join us again on NASENI Milestones next week and be part of homegrown technology. My name is Kierian Umeayo. We thank you again for watching, and goodbye.